Hi, my name is Anuj and welcome to this presentation on predictive analytics of active learning-based education. Imagine the last time you were in a classroom. Was it dull, boring? Were you lost? Unfortunately, the traditional teacher-led classroom model has been the norm since the advent of university-based education. It is rigid, it is direct, and it's very passive. In a world where computers and connectivity are ubiquitous around us, in a world where the needs and skills of tomorrow are being displaced because of automation and globalization, the traditional learning model certainly needs to be rethought. And this poses a big question: what is a learning model that is capable of delivering high performance as well as scalable to the wide needs of students? In this thesis, we answer that question, starting off with an introduction. Even though the traditional learning model is not catered towards the needs of 21st century education, we certainly see an evolution of learning models in the form of blended learning, flipped classrooms, personalized learning, and MOOCs. The future of learning in the industry is also spread on a wide spectrum. On the traditional side, we have companies like School that have a traditional brick and mortar physical presence, but they personalize education for the students. And we have Duolingo on the other side that uses a completely online crowdsourced platform to help students learn a new language. To answer our question, we take the sample of a class on engineering, computation, and data science taught at MIT. We try to develop a blended learning model coupled with learning analytics, and we try to figure out the infrastructure needs for the course. We try to identify the dynamics that have been played during the duration of the course. And we try to figure out how can we use the data collected to create a predictive model. The literature review for this topic focuses on two concepts. The idea of blended learning is a teaching paradigm that involves a mix of face-to-face interactions along with instructional material that is distributed through an online medium. Learning analytics is the collection and measurement of data such that the insights gained from the data can be used to improve student outcomes and optimize student learning. Blended learning itself is essentially a merger of the traditional form of learning coupled with the advances that have been made in the distance education field. Learning analytics sort of stems from research conducted in a multitude of various fields. You have academic analytics, which uses the data from learning management systems and historical performance data of students to identify trends and patterns. Educational data mining uses large data sets to again identify trends and patterns. Recommender systems are widely used in the consumer industry to help figure out similar products based on past historical data. And a few examples of learning analytics being employed in the real world. Course Signals at Purdue was developed as a means to improve student success. They take in data from learning management systems, student characteristic data, as well as prior historical performance of students to kind of bucket the students into three risk categories. The higher the risk pool, the greater the chances of them failing the course. And in case of such an event, the notifications would be sent out in the form of emails, text messages, and even face-to-face interactions with the instructor. Another study that involved learning analytics was at Stanford, where they were able to identify the states that students were in as they went through an open-ended programming task. And based on the states, the instructors were able to give them additional documentation as well as provide code snippets to help them improve their outcomes. In another study coming out of Stanford, the students made use of data available from code.org, in which they were able to take code snapshots, transform them into abstract syntax trees, and put them into a recurrent neural network along with a long short-term memory module to identify future potential on exercises. The course referred to in this study is known as Engineering, Computation, and Data Science, and it focuses on three fundamentals: building programming syntax and foundation, building an intuitive sense of data science and machine learning, and building an expertise in web services and libraries. All this in order to equip students with the skills and tools that are necessary for building full-fledged web applications. The system design of this course is broken up into four parts. The first part is around blended learning, and it itself is broken down into 4 tiers. We have the teaching tier, which involves creating videos, presentations, and lectures. We have the practice and understanding tier, which comprises of exercises, homeworks, and quizzes. These assignments are powered by a DevOps mechanism that helps us capture data. The data is then used for automated grading purposes, performance visualization, and building a predictive model. The hope is that the model can be used as a tool of feedback to the instructor such that they get a deep understanding of teaching quality, material difficulty, and student performance, with the hope that the content could be altered in order to improve student outcomes. The minimum instruction is JavaScript. JavaScript today has wide support on the front end as well as back end, thus enabling students to create applications using the full stack. The philosophy of DevOps is an idea to use agile methods when it comes to managing and pushing production code. We make use of version control in the form of GitHub. Mocha and Chai powers our test development suite. We use Travis CI for continuous integration, and our data pipeline is powered by Gulp, Express, and MongoDB. The curriculum involves having a bunch of preparatory videos in the form of bite-sized video lectures. We have mini lectures and active learning exercises that happen during the bi-weekly meetings. We have homeworks that are passed on as weekly assignments. We have 2 term quizzes, and there's a final project. Access to content was done through a website created solely for the purposes of this course. The feedback loop was in the form of giving feedback to the students as well as the instructors. The students get feedback through an IDE in the form of code hints provided by the code linter. We also have the test suite that provides feedback to the students in case tests are passing or failing. For the instructors, they can use feedback obtained from Google Analytics based on the lecture and video clicks, as well as the admin dashboard, which ties into the performance of the students as they are working through their assignments. This is an example of the code linter. As you can see, there is a hint saying that this particular variable is not being used. Here's an example of the TDD feedback. As you can see, we have 2 passing tests, but in case it's a failure, the same would be highlighted. This is another form of feedback given to the students in the form of a pull request that is made on GitHub. If all the tests pass successfully, it has a green check mark. This is the admin dashboard for the instructors, where we can see the exercises as well as the individual performance on the exercises, and we get a sense of how many tests are passing, how many individual exercises within the tests are passed. The repository itself is constructed in a very similar fashion for the exercises, homeworks, and quizzes. There is a starter code folder. The starter code folder has a test folder which involves and contains the tests that are necessary for this assignment. We have the exercise.js file that contains the boiler starter code for the assignment. There's a run.html to help students visualize the output of the exercises. And the rest of the files are essentially to support capturing data as well as helping push the assignments back to GitHub. The submission process for the students works in the following manner. The students first fork the repository onto their own accounts, they then clone it and download it on their local machine. They then work locally by writing code and running the test on their local machine. Once they have finalized the test, they can add it to GitHub, they can commit, they can push, and once they are thorough with the final solution, they can create a pull request and submit it for final grading. The data collected is in the form of a JSON object, which involves identifying parameters as to who the user is, as to what repo and what exercise is being currently tested. We capture the statistics on how many tests pass, how many tests fail, and in some cases we also capture the source code and try to identify where syntax errors are made. The student demographics for this course comprised of a diverse cohort. There was a good mix of grad students and undergrad students hailing from the fields of engineering, management, and architecture. Most of the students did not have or had less than 1 year of prior programming experience, and the majority of students had no experience working with JavaScript. In terms of the number of runs that were run by the students, the homeworks had the maximum number of runs, and as the students progressed throughout the semester, we saw them performing runs with more confidence before they were submitting it for grading. In this snapshot, we show the percentages of students who were able to pass all the tests for a particular assignment. The average accuracy throughout the semester was around 80%, with a few students failing a few tests every now and then. For the prediction strategy, we could make use of the supervised pattern or the unsupervised pattern. With a supervised pattern, we would be able to predict an exact grade or an exact percentage of the student, and in the unsupervised fashion, we would be able to group students into buckets such that each bucket represents their capabilities or their outcomes. For the purposes of this study, we make use of a neural network with multiple layers. Each neuron in one layer is connected to the next layer through a set of connections that have weights, and these weights are modified up till the network is trained with utmost confidence. To identify the input features, we make use of two categories. We have the user attributes that comprises of information regarding the user's prior experience, the amount of effort they put in, the department that they were in, and then for the assignment statistics, we take into account all their runs for each of the assignment exercises and compute a score. The output labels again can be of two forms. Using the classification methodology, we could give a grade to each of the students, and using the regression method, we could give a final percentage for each of the students. And the training testing flow would be as follows. We would have a bunch of input points. Each input point would have the user attribute, the assignment statistics, and a final grade. And these input points would be fed to the neural network for training purposes. Eventually, when an unknown input point came in with a user attribute and an assignment statistic, we would be able to predict the final grade for that student. The implementation for the neural network makes use of Keras and scikit-learn. We first go through the data manipulation process where we transform the raw data into a matrix that can be split into a training and testing set. We feed that data into an experiment that we create, which has a pipeline to perform a grid search cross-validation training process for us in order to identify the best network with the best accuracy score. The results from the experiment show that a wider network is not necessarily suitable for improving the error rate, and a deeper network is definitely more suitable for improving the error rate. So over here we see that a network with around 100 neurons and one layer performs the best. The number of epochs required for the training process is higher the better. As we see over here, the higher the number of epochs, the lower the error. And in terms of the training rate, a higher rate definitely helps to speed up the training process, but we notice that beyond a certain threshold, the training rate doesn't help to improve the training process anymore. In conclusion, what we describe here is a model where we implemented blended learning coupled with learning analytics to help create a feedback loop where we have data capture and we have a funnel to improve student outcomes. Certain improvements in the methodology would be to log code at each and every change that is made on the student's platform. We should also capture comments and feedback that could be eventually used to feed as a data input into the neural network. We should capture web analytics that take into account contextual behavior regarding the students' habits. And we should design content such that it caters to the needs of the individual students. All in all, I would like to thank Dr. Abel Sanchez for his support for the thesis, the core staff of the Engineering Computation Data Science course for their help and support in implementing the features and functions that were required for this documentation, the people at the IDM program, as well as my friends and family. Thank you.